20. Our primary knowledge of electricity, in its quantitative aspect, is founded upon the observation of the mechanical forces experienced by an electrically charged body, by a magnetized body, and by a body supporting electric current. In the study of these mechanical forces, we are led to the more abstract ideas of electric force and magnetic force, apart from electrification or magnetization, or electric current to work upon and produce visible effects. The conception of fields of force naturally follows, with the mapping out of space by means of lines or tubes of force definitely distributed. A further and very important step is the recognition that the two vectors, electric force and magnetic force, represent or are capable of measuring the actual physical state of the medium concerned. From the electromagnetic point of view, when taken in conjunction with other quantities experimentally recognizable as properties of matter, showing that different substances are affected to different extents by the same intensity of electrico or magnetic force. Electric force is then to be conceived as producing or being invariably associated with a flux, the electric displacement, and similarly magnetic force as producing a second flux, the magnetic induction. If E be the electric force at any point and D the displacement, we have D equals C times E. And similarly, if H be the magnetic force and B the induction, then induction B equals permeability or inductivity mu times magnetic force H times H. Here the ratios C and mu represent physical properties of the medium. The one U, which indicates capacity for supporting magnetic induction, is its inductivity, whilst the other, indicating the capacity for permitting electric displacement, is its permittivity. Otherwise, we may write electric force E equals displacement flux D over permittivity C. Magnetic force H equals induction B over permeability or inductivity mu. And now the ratio 1 over C is the elastivity and 1 over mu is the reluctivity or reluctancy. Sometimes one way is preferable, sometimes the other. Electric and magnetic energy. 21. All space must be conceived to be filled with a medium which can support displacement and induction. In the former aspect, only it is a dielectric. It is, however, equally necessary to consider the magnetic side of the matter, and we may, without coining a new word, generally understand by a dielectric a medium which supports both the fluxes mentioned. Away from matter, the medium concerned is the ether, and mu and C are absolute constants. The presence of matter, to a first approximation, merely alters the value of these constants. The permittivity is always increased, so far as is known. On the other hand, the inductivity may be either increased or reduced, there being a very small increase or decrease in most substances, but a very large increase in a few, the so-called magnetic metals. The range within which the proportionality of flux to force obtains is then a limited one, which, however, contains some important practical applications. When the fluxes vary, their rates of increase .B and .D are the velocities corresponding to the forces E and H, provided no other effects are produced. The activity of E is E.D, and that of H is H.B. The work spent in producing the fluxes is, therefore, U equals integral between 0 and D of EdD, and T equals integral HdB, where U is the electric and T the magnetic energy per unit volume. When mu and C are constants, these give U equals half Ed equals half C E squared, and T equals half HB equals half mu H squared. To express the energy stored in the medium, electric and magnetic respectively, when mu and C are not constants, the previous expressions in equation 5 will give definite values to the energy, provided there be a definite relation between a force and a flux. If, however, there be no definite relation, the energy stored will not be strictly expressible in terms simply of the force and the flux, and there will be usually a waste of energy in a cyclical process, as in the case of iron, so closely studied by Ewing. This does not come within the scope of a precise mathematical theory, which must of necessity be a sort of skeleton framework, with which complex details have to be separately adjusted in the most feasible manner that presents itself. Elotropic relations